Hello, and welcome to the fourth lecture of Physics 363, Intermediate Classical Mechanics. Today we're going to be talking about Lagrangian multipliers and how to use them to impose constraints, both in general maximization, minimization problems, but then specifically in problems that we're going to be writing down and solving using variational principles. Before we get into the lecture, let me just remind everybody that the first problem set is due tonight at 11:59 p.m., so midnight Eastern Daylight Time. I'm not going to check the Dropbox until Friday morning, so if you have it before I check before I check it Friday morning, I will accept it at full credit. Key concepts to be looking for in part 1 and 2 of the lecture today are Lagrange multipliers, definition, what are they, how they're defined or what they mean as geometric conditions or geometric objects, and then how to impose them in variational principles for integral constraints, so constraints that are defined across the full range in time, and local constraints, constraints that are true at each individual time, and we'll make that explicit when we get to it. By way of review, remember that when we talked about constraints in the first lecture, we talked about two specific categories, holonomic and scleronomic constraints. Holonomic constraints are constraints that can be written just in terms of the generalized coordinates, and scleronomic constraints are those constraints that are constant in time or independent of time directly. That is to say, a scleronomic and holonomic constraint can be written as this expression over here, some function g is equal to g of q is equal to 0. Okay, so all the constraints that we're going to apply today using Lagrange multipliers are necessarily going to be of this class. It doesn't have to be that case. We could apply Lagrangian non-holonomic and non-scleronomic constraints using Lagrange multipliers. But just to simplify things today, all the examples we're going to be doing look like this. The second thing to recall is that when we have a integral condition that we want to find stationary states of, minima, maxima, saddle points of, that looks like this. It has some integral, we called it s, from time 1 to time 2, over time of some known function a priori of the coordinate, its time derivative, and time, that this was made stationary if these coordinates satisfy the Euler-Lagrange equations. And we had two kinds of Euler-Lagrange equations that we derived. The first kind, which is the one that we've been using mostly to date, okay, so a time derivative of the partial of f with respect to q dot minus the partial of f with respect to q equals 0. But the second kind, which we also mentioned in lecture 2, which rearranges things slightly and is particularly useful if f is independent of time. Finally, all the way back from the first lecture, let me remind everybody about symmetry and the relationship between geometric objects. Okay, so the idea that if we can write some statement down as a relationship between scalars, or a relationship between vectors, or a relationship between tensors, those statements obey the symmetries associated with rotation, parity, and also general coordinate transformations. So these statements are independent of coordinates, and that's one of the things that made them very, very attractive, because we didn't have to appeal to a special coordinate system. That's something we're going to use in our discussion of Lagrange multipliers. Okay, so let us begin with Lagrange multipliers, and I'm going to begin actually again with an allegory. So we're going to talk about the case of the poor sheep farmer. Whose flock is wandering all over the field, all over Waterloo, okay? And so he needs to have some place to put his sheep. He needs a sheep pen. And at first, let's imagine that this pen is rectilinear, okay? So it's some sort of rectangular structure. And because he has some number of sheep, he needs to have this pen cover some known area. That is, it has to cover a fixed area. But he has some freedom in how he arranges this pen. Okay, he can adjust its length and he can adjust its height, or length in one direction and length in the other direction, to change the perimeter of it. And because he pays for the fence in dollars per meter, what we really want to do is minimize the perimeter. Okay, so we want to fix the area and we want to minimize the perimeter p. And this is a classic constrained minimization problem. Okay, or constrained extremization problem. We want to adjust our parameters, but subject to a fixed condition. If we were going to write these things out in slightly more formulaic ways, we would say the area, which is in this case x times y, where x is the horizontal length, or the length in one direction of the fence, and y is the width of the fence. This guy is constant. Okay, but the perimeter, which is 2 times x plus 2 times y, is what we want to minimize. Well, the first thing is, this really looks like a 2D problem, but is it really? Okay, so it looks 2D, but we have a constraint. And if you recall, when we were doing coordinate counting or degrees of freedom counting, we would count up the coordinates we had, and then we would subtract off the constraints. And in that way, we found that this sort of problem would be a 1D problem. Okay, and we're going to solve this problem, in fact, 4 different ways. And the first way we're going to do it is just by imposing the constraint from the outset. That's sort of the standard way. So we're going to solve this in 4 ways. So keep track of the various ways we're doing it. We're going to get through 3 in the first part of the lecture, and the 4th one we're going to talk about in the second part. So the first way to do this, sort of the standard way, the way that you may learn in an intro course to calculus, is simply to say, well, there's going to be a relationship between x and y imposed by my constraint. That is, y is just going to be the area divided by x. If I say that's true, then it is always true that x times y is equal to the area. Okay, it's always true that my constraint is satisfied. Okay, this implies, or I could just plug this into the perimeter formula. It implies the perimeter is given by 2x plus 2 times the area divided by x. And now I have a manifestly one-dimensional problem. I have this one degree of freedom x that I can vary, and that's going to tell me what the perimeter is. And because it's a 1D problem, we know exactly how to solve it. So it's manifestly 1D, we know how to solve it. We know that we just take the derivative of the function with respect to our independent variable. In this case, this is 2 minus 2 times a over x squared, and we set that to 0. Right? And recall we said this was like taking the first variation of our function, looking at the first term in the Taylor expansion of our function, and setting it to 0, forcing it to vanish. So I can solve this, and we get that x squared is equal to a, or x is equal to the square root of a, and y is equal to the square root of a as well, because it's just a divided by the square root of a. In other words, our poor sheep farmer finds that it's hip to be square, right? So we want to have a square sheep pen. That is the optimal configuration. Okay, many of you may have already known that. The second way we might try to do this is with an explicit coordinate transformation. So this first way, we did relate y to x, and then we went through a procedure to solve for the optimal x and got some answers. But another way we might do this is try to convert to a convenient set of coordinates. Okay, and that's really going to suggest another way to look at the underlying problem. And the coordinate transformation that we're going to want to make is to hyperbolic coordinates. I'm going to write down the definition in just a second. Okay, so hyperbolic coordinates, for which we have u is equal to the natural log of square root of x divided by y, and v is equal to the square root of x times y. And you'll recognize that this v is really just the square root of the area. Okay, so this hyperbolic set of coordinates is a special set of coordinates in which one coordinate is just equal to the area. Okay, the inverse transformation, which we're going to need, is x is equal to v times e to the u, and y is equal to v times e to the minus u. Okay, and this is true for x greater than 0 and y greater than 0. And our poor sheep farmer, would like to have his pen have positive width and positive length. Okay, so in terms of our new coordinates, we have the perimeter is still equal to 2x plus 2y. The perimeter is a scalar, so it's just whatever value it is at x and y corresponding to those u and v. And that means it's 2 times v e to the u plus 2 times v e to the minus u. Okay? That's just inserting these expressions down here into the perimeter expression. Okay? Now, if I were to try to draw a picture of what this P of u and v looks like, this is a little bit hard because it's a two-dimensional function, but I'm going to give it my best shot. So let's put u along that direction and v along that direction. So this is, let's simplify it just one more step, 2v e to the u plus e to the minus u. Okay? At v equals 0, our function is 0. Okay? It's linearly increasing with v, so the u equals 0 line is stepping up linearly with v, but it goes exponentially with u in each direction. Okay, so up here, it's gone way up. Up here, it's gone way up as well. So it might be linearly increasing with v, but it's really increasing a whole heck of a lot near the edges with u. Okay, so it looks like a piece of paper that's being curled up. Now, when we say that the area is constant, when we say that the area is fixed, we're really saying that this v coordinate is fixed. Okay, right? That's just the area is constant, because this v coordinate is just the square root of the area. And so that means that when we talk about trying to optimize this for our poor sheep farmer, we're going to want to take a slice at constant v through this function. That is to say, we are going to want to take a slice at some fixed v. And in that fixed v slice, we can already see the right answer is going to be in the middle just because we drew it. But let's try to prove that. Okay, so we want to maximize this at fixed v. So we're saying, I'm sorry, minimize the perimeter P of u at fixed v. And we're going to fix it to the square root of a. Again, we know exactly how to do that. We're going to take the partial derivative of p with respect to u. Why partial? Because we are fixing the v coordinate. And that's going to be 2 times v times e to the u minus e to the minus u. Right, that minus sign just came down. And that has to be 0. Now you can look at this, and I think everyone will see immediately, or we can go through and solve it, but you can look and see immediately that this implies that, in fact, our intuition over here was exactly correct, that u is 0. Right? E to the 0 minus e to the minus 0 will vanish. Okay? So that implies u is 0. All right. What does that mean for x and y? Well, we have x was v e to the 0, which is square root of a, because remember we are solving it at v equals the square root of a. And y, similarly, is v e to the minus 0 minus u at this maximum, and that's equal to, again, the square root of a. So we found exactly the same result. We want to build a square pen, but we've now done it with this coordinate transformation where we chose one of the coordinates so that it would be constant. Note that even though we have the partial of p is 0, we might ask, well, what is the partial with respect to v? Okay, what does dp dv look like? Well, dp dv, just looking at this up here, is equal to 2 times e to the 2 times e to the u plus e to the minus u, and plugging in at u equals 0, so plugging in our point, this is equal to 4. This is not 0. Okay, so while our favorite point was indeed uv 0 square root of a, this point does not satisfy the more general condition that the gradient of p, the gradient of our perimeter located at 0 square root of a equals 0. Okay, so it's not actually a maximum or a minimum of the perimeter generally. It's you know, it's sort of a minimum in one sense and not in another. Why? Okay, why is the standard way of doing this not helping us out? Well, let's think about the constraint. And in fact, that's going to be the answer. The reason why the gradient is non-zero is because we have a constraint. Well, our constraint is that v squared minus a equals 0. Okay, and let's write this now in the form that we discussed about holonomic and scleronomic constraints earlier. Let's call this thing g of u and v. Okay, there's no u, so the u dependence is trivial. It just depends on v. We're going to call it g of u and v. So we have this extra constraint that looks like, in fact, it is exactly a holonomic and scleronomic constraint, right? Okay? And the gradient of this guy, gradient of g, which is telling us the direction perpendicular to where it's satisfied. It's telling us the direction in u and v space in which to move orthogonal to lines of constant constraint. Okay? This is equal to, and I'm just going to remind everyone, this is partial g, partial u, partial g, partial v. This is equal to 0, because it doesn't depend on u, times 2v. Okay? And this is the direction. It's the direction in uv space that's perpendicular to constant g. Okay? And in particular, g equals 0. Okay? And you'll note something kind of interesting here. The way in which this is true, the way in which we fail to have a vanishing of the gradient of the perimeter is exactly the way in which this gradient is non-zero. Okay, the gradient of the constraint is non-zero. Okay? So let's be a little bit more explicit about that. If we were to look at our function, or our constraint function, in u and v space, u and v, and look at lines of constant constraint. Okay, so these are g, u, v is constant. Okay, the gradient we said was perpendicular to that. Okay, what we're really doing is we're saying we're going to allow our function to slide around. We're going to allow our perimeter to slide around back and forth along the constraint, okay, but not slide perpendicular to it. Okay, so we are going to minimize our function on constant lines of constant g sliding back and forth, but not allow it to move up and down in this picture. And as a result, the piece of the gradient of the perimeter that's perpendicular to the gradient of g has to vanish. Or equivalently, the gradient of the perimeter has to be proportional to the gradient of our constraint. Okay, and this lambda, this is a constant of proportionality. And it gets a name. It is a Lagrange multiplier. Okay, and this is really just saying that we can slosh around all we want along the constraint on lines of constant constraint, but not across it. Okay, so we can move in the green direction, but we can't move in the red direction. So this has to be true for some lambda. I haven't said what lambda is, what value it is, but some lambda. In our example, we said grad p was equal to 0 and 4. Okay, this was at our happy minimum. This was at u of 0 and v of the square root of a, right? this is what we said the minimum fence price was. And this has to be equal to whatever the lambda is times the gradient of our constraint of g. So that's lambda times 0 and, looking back, 2 times v, or 2 times the square root of a. Okay, and again, this is just lambda times the gradient of g at u of 0 and v of square root of a at the same place. Okay, so this is clearly satisfied if this is true, if lambda is equal to 2 over the square root of a, which is perfectly fine. Okay, we didn't say what lambda could be. That's the value of lambda, and then our vector equation is satisfied. Okay, so how does that help us? That seems like a lot of complication just to come up with another way to solve a problem that we already knew how to solve. Well, this little trick of changing to a particular set of coordinates and then recognizing that there's a geometric construct that we can write down, okay? This geometric construct that says that the gradient of the function we want to minimize or find the stationary points of is related to another gradient times a scalar is a vector equation, okay? And because it's a vector equation, it's true in any coordinate system. So that brings us to the third way we're going to solve it. And we're going to solve it by the method of Lagrange multipliers. Okay, we've already done most of the work, so this one's actually going to be quite fast. Okay, so it's just recognizing that grad p equals lambda grad g has to be true for all coordinates. Okay, because it's a vector equation. Because it's a, vector is equal to vector equation. Okay, so let's do it in x and y directly. So we said p of x and y is equal to 2x plus 2y. So that means that the gradient of p, which now is partial p partial x, partial p partial y, okay? So since we're doing this in our original coordinates, the gradient takes its original coordinate meaning, and that's going to be 2, 2, okay? And our constraint, g of xy, is equal to xy minus a, okay? That's the thing that we want to be 0. And the gradient of g then, partial g, partial x, partial g, partial y, is equal to, well, the derivative with respect to x is y, and the derivative with respect to y is x. Okay? And so our condition that the gradient of p is equal to a constant times the gradient of g gives us two equations. It gives us 2 is equal to lambda times y, and it gives us 2 is equal to lambda times x. And our constraint equation gives us one more, xy is equal to a. Okay, that's our constraint equation. Okay. Let me shrink this down so we have a little bit more room. Okay, so our condition that the gradient of p is equal to lambda times the gradient of our constraint gives us two equations. 2 is equal to lambda times y. That's the x component of the equation. And 2 is equal to lambda times x. That's the y component of the equation. And then we have one supplementary equation that comes from our constraint itself. Xy is equal to a. Okay? And this really just comes directly from the constraint. This is just g is 0. Okay, we can solve these directly. These first two are going to give us y is equal to 2 over lambda, and x is equal to 2 over lambda. And this last one we can solve directly. It's going to then give us that 4 over lambda squared is equal to a, or 2 over lambda is equal to the square root of a. Okay? And that's, of course, just what x and y were. So we once again get that x is equal to square root of a, and y is the square root of a. And our shepherd should have a square pen if he wants to keep his costs manageable. Now, before we move on to talking about how to do this in a variational situation, or variational calculus situation, applied to variational principles, let's note one more thing about this method of Lagrange multipliers that we've already developed. Okay. That is to say that Lagrange multipliers effectively are increasing the number of degrees of freedom, or the dimension of our problem. Okay? That is to say, the way in which we wrote down the solution is equivalent to minimizing or finding the stationary points of a new function for the perimeter. That's now a function of 3 variables, which was equal to our original expression for the perimeter minus our Lagrange multiplier times our constraint. Okay, so here we have 3 dimensions, 3 coordinates. And over here, we only had 2 coordinates. Okay, so how is this the same? Well, in terms of these 3 coordinates, the gradient of our new function is partial p tilde with respect to x, partial p tilde with respect to y, and partial p tilde with respect to lambda. Okay, where each of these partial derivatives are holding the other 2 of x, y, and lambda fixed. Okay, and what do these look like? Well, let's look at these first 2 equations. These first 2 equations are just what we had before said was the gradient of p minus, all of these have to be 0, right? So 0, 0, 0. Gradient of p minus lambda times the gradient of g equals 0. And this last equation is just minus g of x and y is equal to 0 as our constraint. So writing this new function of 3 coordinates, not our original function of only 2 coordinates, but adding an extra coordinate in the form of this Lagrange multiplier, has allowed us to create a something that looks identical to the normal procedure that we would have followed for an unconstrained optimization, unconstrained function, stationary points of an unconstrained function. Okay, so this is, in our case, 2 equations plus 1 constraint. Okay, and since we've already solved this problem many times this way, 3 times this way, we won't have to do it again. This is just a conceptual description of what we had done. This addition of additional parameters, the increase in the number of parameters, is exactly what we're going to do when we talk about Lagrange multipliers and the application of constraints in variational principles. Lagrange multipliers, and variational principles. Now, we're going to talk about 2 classes. Okay, and the 2 classes are going to be integral constraints and local constraints. So let's talk about integral constraints first. And what do I mean by that? Okay, I mean we have a constraint that looks like g, integral across our entire time domain dt, of some, and I'm going to assume here it's holonomic and scleronomic, just for convenience. We don't have to. We could go through this process, permitting it to depend upon q dot and time if we like. I'm going to assume that this is fixed. And when we talk about some examples in part 2 of the lecture, we'll give explicit cases where we have something that's being integrated across time or across the independent variable that we would like to hold fixed. Okay, but there's some integrated thing that we're holding fixed. So that's what I mean by integral constraints. Okay, so g of q doesn't have to be 0 everywhere, but its integral has to be 0. Okay, in this case, our coordinates go from this one function of time, and I'm going to explicitly indicate that it's a function of time, to our generalized coordinates plus one dimension. It's a constant. Okay, it's not a function of time. Okay, that's a constant. And we have one constant because we have one constant constraint in what we're writing down. So the strategy is going to be identical to what we did in that last version of the Lagrange multipliers. We're going to define a new integral quantity, s, a new functional, which is our original functional plus our Lagrange multiplier times g. And expressing this in terms of the integral, this is f of q dot t plus lambda g of q. Okay, so this part here, this was the thing that gave us s, and this part here was the part that gave us g, and we've just combined them inside the integrand. Okay, so now let's consider variations. And I mean our first order variations of this s tilde. And the first is going to be with respect to q. Okay, so it's going to be variations in the function q and q dot. Well, the answer to that is the one we already know. These are just the Euler-Lagrange equations. Okay, and they look like, as we've written down before, d by dt partial f partial q dot, and it's f by q dot only because it's the only one that depends on q dot inside the brackets, minus partial f partial q, that's the first part, minus lambda partial g partial q, and that's the second part. Okay, so this s tilde, we might think of it as being defined in terms of a f tilde of q dot, and time, which is equal to the sum, right? And we're just writing down the Euler-Lagrange equations for this f tilde. And that equals 0. Okay. The second set of variations are with respect to lambda, because now we've elevated lambda to a coordinate. Okay, but lambda is a constant, it's not a function. Okay, and we could go through the process of permitting lambda to vary as a constant and asking what the result is, but this is really just taking a derivative. Okay, so this is just taking this derivative. The partial of s tilde with respect to lambda is equal to 0, and that's just our desired integral constraint. Okay, so we have our constraint, and we have an expression for the Euler-Lagrange equations that's modified slightly. Okay, so this is the modified piece, and this modified piece actually looks very, very similar to what we had before. We said that the thing that, when we said the gradient of something is no longer 0, is equal to this Lagrange multiplier times the gradient of our constraint. Well, that's essentially what we found, something that looks very similar to that. Okay, and so we're going to do some examples in the second part of the lecture of exactly that procedure. What if we have a local constraint? So what I mean by a local constraint is not that this integral of our constraint function is fixed, but actually that our constraint function itself is 0 at all time. Okay, so this is a little bit different than the integral constraint. because we have an infinite number of actual constraints being applied here because we're doing it at each and every time. That might sound like it's very, very difficult to include, but it turns out that this is just as simple to include as our prior example. And again, we're going to do it by constructing a new action or a new integral or functional to find the stationary points of with the help of a Lagrange multiplier. So it's going to be our original function, f of q, q dot in t, okay, plus, now there's going to be a Lagrange multiplier, which I'm going to write as lowercase lambda, g of q. Now this guy can depend on time. Okay, so that's different than before. Right, before it was a constant across the whole time range, but now it can actually depend upon time. Okay, it doesn't depend on q, but it can be a function of time. And our coordinates are now q of t and lambda of t. So we've added a full additional coordinate. And so again, we're going to talk about variations of our new integral. And we're going to do it with respect to q. Okay, and when we do it with respect to q, we're going to get something that looks very similar to what we had before. D by dt, partial f, partial q dot, minus partial f, partial q, minus lambda, partial g, partial q, equals 0. So this looks identical to what we had before, except remember, lambda can now depend on time. And then with respect to lambda, and this is going to look very much like another Euler-Lagrange equation, except we do not allow g to depend on q dot. So that means that we just have one term, and that's going to be our constraints. And again, this is at all time. Okay, so this looks, just to compare it with the prior result, we had an integral in our constraint here that appears, and a constant lambda. In our new constraint, lambda depends on time, and this is true at all time. Okay, but otherwise, it's an identical formulation, just putting this additional constraint into the integrand into our functional that we seek to find the stationary points of. Okay, so that wraps up part 1. And in part 2, we're going to apply this in a few different example problems, including the 4th solution to our poor shepherd's conundrum of how does he get the most fence or the most sheep pen for his buck. All right, I will see you on the other side. All right, welcome to part 2 of the 4th lecture. Now we're going to talk about some examples of applying Lagrange multipliers to impose constraints in variational principles. So from the first review, remember the Euler-Lagrange equations of the first kind and the second kind. We will use each of these where most appropriate. Remember that Euler-Lagrange equations of the first kind are easiest to employ when the function in our integral, in the integrand, is independent of q, and the second one is most convenient if it is independent of t. What we learned in the first part of the lecture was that if we had an integral constraint, that is a constraint of the form integral t1 to t2 over time of some constraint function, some combination of generalized coordinates, that this was naturally and easily included in our variational formalism already by simply defining a new integral that included both our original function and our new function of q with this Lagrange multiplier, capital lambda, which in this case was a single number, and expanding our coordinates from our original set of generalized coordinates to generalized coordinates plus this one number. If we had a local constraint, okay, so the integrated constraint is the integral 0, a local constraint is at every time it's 0, then we do exactly the same thing. In fact, these two expressions, two lines look identical, except now this Lagrange multiplier is can be a function of time, and so I wrote it as a lowercase lambda just to make that explicit. Okay, so let's do some examples. And the very first example is going to return us to the poor shepherd. Okay, right, so he wants to find the cheapest way to pen in his flock. Now, our poor shepherd is particularly educated, being living near the city of Waterloo. I think he attended the University of Waterloo. And so we are going to extend beyond. So we are going to extend beyond rectilinear pens, beyond rectilinear. Okay, we're going to say that our shepherd has the freedom to make any shape pen he likes. And he can try to save money by arranging this pen. And to define this pen, just to be explicit about it, let's choose an origin. And let's specify in polar coordinates the location of the pen itself. Okay, so there's some fiducial direction, theta and r, and the pen is then defined by a function of r as a function of theta. Okay, so our shepherd can specify the radial location as a function of polar angle of where the pen is, and we are going to traverse or move around our pen shape in that way. In this picture, our perimeter now, well, let's start with our area. Our area now is the integral from 0 to 2 pi over that polar angle of 1/2 r squared. Okay, so we're just adding up all the wedges. Okay, all the wedges around the pen. Okay, and this is the part that has to be fixed or constant. The perimeter is a little bit more complex than before. Integral from 0 to 2 pi, again, about our polar angle. But now, it goes as the square root of r squared plus r prime squared. Okay, now if you recall our geodesic, where is this coming from? This is just saying it's the integral of dr squared plus r squared d theta squared. Okay, and that's equal to the integral d theta times dr d theta squared, that's r prime squared, plus r squared. Okay, so it's very similar to what we were doing for our geodesics. Okay. So what is our combined integral? Our p tilde is going to be equal to p, in this case it's a functional of r, plus lambda, right, some overall lambda, times a, minus, let's say a naught is the target area, because we gave this expression a name. And just to simplify matters, I'm going to put in a 2. It's just going to make the equations a little bit easier to look at. Okay, this is just to simplify. Okay, since lambda takes on whatever value it needs to, putting an extra 2 in front of it doesn't change the condition, right? 2 times a minus 2 times a0 equals 0 is the same thing as a minus a0 equals 0. Okay, it didn't show up in our prior expressions. That's why I wanted to highlight that. All right, so then this combination is 0 to 2 pi d theta square root r squared plus r prime squared plus lambda r squared. And those are 2. It really just got rid of that 1/2. Minus lambda a naught, and it's going to turn out that that constant isn't going to affect anything at the end of the day. Okay, so I'm just going to keep it around for now, but it won't matter. Okay, it's formally necessary to get our area to be fixed to A naught, but we're going to see it's going to drop out of all the equations we write down for R. Okay, so our Euler-Lagrange equations are just, we're going to do the Euler-Lagrange equations of the second kind. Okay, and so that's going to look like d by d theta of square root r squared plus r prime squared plus lambda r squared, okay, that's f, minus q dot r prime times partial f partial q dot r prime divided by r squared plus r prime squared equals 0. Okay, so this was f, and this is q dot df q dot, and there's the minus sign. Okay, there's an extra term that's 0 out here, which I think I forgot to write on the review slide, which is a df d theta. Okay, right, and this is why we're using the Euler equations of the second kind. Okay. I like this equation. Again, as I say often, this is an equation even I can solve. Because this differential equation, we have a derivative of a thing is equal to 0. And so this thing inside the derivative has to be constant. So we can integrate this in one step and say that it's a constant. Okay? And I'm also going to simplify this. I'm going to combine the first term, and I'm going to combine the third term. Okay, notice that this is r prime squared. And so that's going to allow me to combine these and put them into a single term, which looks like r squared divided by square root r squared plus r prime squared. Second term, lambda r squared. And this is equal to a constant. And we're going to call that k. Okay, this is just integrating. Okay, and this k is our first constant of integration. Okay, so that's something that we're going to have to know how to set. And of course, we have our Lagrange multiplier sitting there. So at this point, I'd like to solve this equation for r prime, get a differential equation for the radius. I'm going to bring it back over here so that we have it on our next page. Okay, so now we're just going to solve for r prime. And when we solve for r prime, I'm just going to write the answer. It's a small amount of algebra. And I'm going to write the answer in a particular way. And you can check that this is in fact the same thing. Okay, so there we go. We solved for r prime. And now we have an ordinary differential equation for r of theta. Okay, so now's the time to go off and integrate the, as mathematicians would say, integrate the ordinary differential equation, solve the ordinary differential equation for r prime. But I'm going to say stop and think. Okay, this is physics, right? And so let's before we just go off and turn the mathematical crank, think about what kind of solutions we might have to this ordinary differential equation. And there's one that's very clear, and that is, if the right-hand side vanishes, then r prime is 0, and r becomes constant. Okay, that is to say, if r squared minus k minus, I said little lambda. That should be, where did little lambda come from? This should be capital lambda. Okay, if r squared minus k minus lambda r squared squared is 0, then r prime equals 0, and r is constant. Okay, and that is the solution, right? Because in this equation, this is an algebraic equation. This is an algebraic equation for r in terms of constants. K and lambda. Okay, so we really only have constants in this equation. And so there is a value for constant r for which this is true, for all theta, as long as r is constant. Okay, so we've solved this equation without even having to write down a general solution. We know there is a solution, and that solution is r is constant. Okay, that's my favorite kind of way of solving an ordinary differential equation. I call it that's the Russian way, right? First write down problem, then write down solution. At least it's the way that Landau and Lifshitz follows. If r is square root of a naught by pi, okay, then it's a solution. So if it's a constant, then r of theta is a solution to the Euler-Lagrange equation and the constraint. Okay? Of course, this immediately raises the question that's most on the mind of our shepherd. Is this a minimum? Okay? The answer is yes. But I'm going to let you check. Okay? So you can go through and add small changes to r and ask what that does to the length. But yes, this is necessarily a minimum, but I'll let you check that. Okay. Note that we have our solution for r, and we found that the answer that the shepherd is looking for is not a square, right? The answer for our shepherd is he wants a circular pen. That's going to give him the most area, the minimum cost for generating for buying the fence. Okay, so he wants a circular pen, constant radius as a function of theta. Maybe more seriously, what we've just done is demonstrate that a circle is the two-dimensional geometric shape that has the minimum perimeter for a given area. I think that kind of thing's pretty cool. We're able to actually prove that, something that I think many of us may have already known from experience, but we were able to prove that explicitly using calculus of variations. Okay, a second example that I want to do, and now we're going to move beyond sheep, and we're going to talk about laundry. We're going to talk about a clothesline. Okay, and we're going to talk about the shape that a clothesline takes when hung between 2 points. And this sounds very familiar. I hope it sounds a lot like the first problem set. Okay, so you may find some of the discussion useful if you're still working on it. But imagine that we have a clothesline that's connected between 2 points. Those 2 points are fixed. Okay, and it has a constant density per unit length, or mass per unit length. Let's call that m. Okay. We might normally call it lambda, but I don't want to confuse people with too many lambdas. And it's feeling gravity. So gravity's pulling it downward. Tension is pulling it upward. And so the question is, what is its shape? Okay. So this is a famous solution called a catenary. Okay. Just like in the problem set, it's going to attempt to minimize its gravitational potential energy. Okay, so the way we're going to find this is we're going to look at minimizing the gravitational potential energy. Okay, why do we know that that's going to be the answer? Well, if it were in any state except for the minimum gravitational potential energy, it could move into the minimum gravitational potential energy and bounce around. Okay, and that would necessarily not be the equilibrium stationary shape that it will have. Okay, so the only way that we have no free energy left to go into motions is if we're at the minimum. So what does the minimum gravitational potential energy look like? Well, let's call it U. This is the integral from x1, let's call that x1, and that x2, over x, of our mass per unit length, times the acceleration constant. Okay, so this is 9.8 meters per second squared, not a constraint function, times 1 plus y prime squared. Okay, this is the length. Okay, so this is dl dx. And it's computed in exactly the same way that we did so for geodesics. Times y. Okay, so all we're saying is that it's mgy times dl. So that's the gravitational potential energy across the line. Now the thing that's going to be very different than the problem set is that we are going to have to keep something fixed. And what we need to keep fixed for our clothesline is the length. It's however long the clothesline was. Okay, we're not going to change that. In the problem set it changes because it falls over the pulleys. But the length is being held fixed here. And the length is a very similar integral. Integral over x from x1 to x2 of just dl. Okay, and this is our constraint. Fixed length clothesline. Okay, so the way we're going to go about solving this then is writing down our modified modified version of u, which includes our constraint. And again, it's an integral constraint. So this is mg y 1 plus y prime squared plus lambda 1 plus y prime squared. And I am going to erase the dl dx because we need the room. Okay, minus capital lambda L naught, and again, this is not going to matter. It's just being kept for explicit, being explicit about the nature of the constraint. We have this L as being fixed to L naught. Okay. Again, our functional doesn't depend upon x explicitly, and so the second form of the Euler equations, or the Lagrange equations, is again going to be most useful, which in this case turn out to be lambda plus mg y 1 plus y prime squared. That should be y prime squared minus y prime squared lambda plus mgy divided by 1 plus y prime squared. And this whole thing, d by dx. And that's 0. Okay? So that's our Euler-Lagrange equation of the second kind. And again, the partial of the integrand with respect to x vanishes because it doesn't depend on x explicitly. And again, this is an equation that I can solve, and it is equal to, the piece inside the brackets is equal to a constant. Okay, that is to say, you can combine terms here and simplify it slightly and get lambda plus mgy times 1 over square root of 1 plus y prime squared is equal to a constant. Okay, and again, this is our constant of integration. Okay. Okay. We can invert this to find what y prime is. Let me copy it and take it over to the next page, just like we did with the sheet pen. Okay, so we can invert this to get an equation, or solve this, maybe I should say solve this for y prime to get an ordinary differential equation in the form that we would like to solve. And we get that y prime, just after some algebra, is equal to 1 over k squared times lambda plus mgy squared minus 1, all to the 1/2. Okay? And we would like to solve this ordinary differential equation, which we can do, so this is again an ODE. Okay, which we can solve by direct integration. Okay, so we're going to say that this is dy dx, and we're going to bring this part over here on the right, over underneath, bring the x up over there, and integrate both sides. And when we do that, we get the x integral, x plus x naught. This x naught is our constant of integration, the second integral. Okay, so just like k. And the left-hand side, which now I've swapped over to the right, is going to be the integral dy of 1 over k squared lambda plus mgy squared minus 1 to the minus 1/2. Okay, that looks kind of like a nasty integral, but we are going to simplify this. We're going to simplify this by saying this stuff is going to be by a change of variables made equal to u squared. Okay, that is to say, we're going to change to the variable u, which is 1 over k lambda plus mgy. And that means that du is equal to mg over k dy. Okay, so it's actually a relatively straightforward change of integrals, change of variable. And in terms of this new variable, this becomes the integral of du times 1 over u squared minus 1 times a constant, which we could have pulled out of the integral altogether. Okay. Now this integral here, you can look up in an integral table, or you can work through additional changes of variables in trigonometric functions. And what you'll find is that it is k over mg times the inverse of hyperbolic cosine, or cosh. Okay, so that's a fairly standard integral to look up. You can put it in Wolfram alpha, or like I said, you can go through additional changes, trigonometric changes of variable, and you'll find this. It's inverse of hyperbolic cosine, or inverse cosh. Okay, and now I have a left-hand side and a right-hand side, and I can solve this for u. Okay, and we just get that this, and insert y and the other constants. And at the end of the day, what we would get is that 1 over k lambda plus mgy, that's u, is equal to hyperbolic cosine of mg over k x plus x naught. Or solving this for y, because after all we wanted y of x, y is equal to k over mg times cosh mg over k x plus x naught minus our Lagrange multiplier divided by mg. And there we have it. We have our solution. We have that the height is expressed as a hyperbolic cosine with some constants involved. Okay? So there's a few things that we have to determine. We have to determine k, we have to determine x naught, and we have to determine the hyperbolic, the Lagrange multiplier. So there are a few quantities that we have to identify. So how do we do that? Let me copy this guy to the next page, and we're going to talk about how we set these. Okay. Well, what conditions do we have? Well, we actually have three conditions. Okay. The first condition is we know that y of x1 is equal to whatever the initial height at y1 is. Okay. The second is y at x2 is whatever the height at y2 was. And the third is that L is equal to L naught. So let's go through these in turn and see how we might practically do this, and begin with the constraint. Okay, so for the constraint, we note that y prime is equal to the derivative of this guy, particularly simple form, hyperbolic sine mg by k, x plus x naught. That is, all the constants drop out. And that means that our integral, L, is equal to k over mg. You can just take this and plug it into the expression for L and integrate. Sinh hyperbolic sine mg over k, x plus x naught, evaluated from x1 to x2. Okay, so this gives us one condition, and it's going to give us a condition on k and x naught. Our first two conditions, which just say that the height at the initial point and at the end point are given by what the initial height and endpoint values are, then depend upon k, x naught, and lambda. Okay, so these are going to depend on k, x naught, lambda, k, x naught, lambda. And this last guy, as we just saw, depends upon k and x naught. So we have our three equations, we have our three quantities. In fact, each of these depend upon exactly the quantities that we need. And in principle, you could go through the process of solving each one of them and getting back what lambda and k have to be. The final example I want to do is something that we are already familiar with. I want to return to geodesics ants on a cylinder. Okay, so if you recall, one of our very first geodesic problems was imagining we had a cylinder and we have 2 points on the cylinder, and we wanted to know what was the fastest line to get from one of those points to the other. Okay, and we found that a helix was the right solution. And in fact, there were many helices that we could have followed. And we did this originally by writing this as a two-dimensional problem. Okay, but now we're going to do it as a three-dimensional plus a constraint problem. Okay, so we ought to find very similar answers, but we want to find them in a slightly new way. Okay, so our solution previously, remember, was that theta, where theta goes around this way, was a function of z is equal to some constant times z plus some other constant, where z describes the distance along the cylinder. Okay, and these a and b were constants of integration. Okay, that are determined by the location of the endpoints of our geodesic. Okay, but in 3D, what does this look like? Well, in 3D, a length in, we're going to use polar cylindrical coordinates in 3D. And in 3D, length is dz squared plus dr squared plus r squared d theta squared. Okay, so we said before that this was 2r in diameter. That's capital R. But we're going to add to our theta and our z a coordinate r, which is the cylindrical radius coordinate. Okay, so we're not always imagining that our line has to be on the surface. It could, in fact, go through the center in principle, but we're going to force it via a constraint equation to live on the surface. And this is dz square root 1 plus r prime squared. Okay, so this is dr dz plus r squared theta prime squared, and this is d theta dz. Okay, our constraint is going to just be r theta z is just going to be equal to r minus capital R. That is to say, we're going to be constrained to live on the surface of the cylinder. Okay, so then our modified functional is the integral from z1 to z2 dz of, now the combination of our length element okay, plus our Lagrange multiplier. And now this Lagrange multiplier has got to be true everywhere. Our constraint is no longer an integral constraint, but our constraint is true at all points along the cylinder, at all values of z. So our constraint, true everywhere, can be a function of z. So I'm going to write that as a lowercase lambda, just to remind ourselves that that's true everywhere, and lambda can be a function of z. Okay, so here's our modified functional. It depends upon r of z and theta of z, and now lambda of z. Okay, so we have 3 coordinates that we're keeping track of. All right, so let's vary with respect to lambda. Okay, that is the Euler-Lagrange equations. Okay, and if we do that, we just get our constraint back. Okay, and you can differentiate that constraint and get that r prime equals 0. And of course, you can solve that constraint and get that r equals capital R. Now let's vary with respect to theta. And again, we're going to talk about an Euler-Lagrange equation. Okay. Now we vary with respect to theta, and our Euler-Lagrange equation looks like d by dz of r squared theta prime divided by square root 1 plus r prime squared plus r squared theta prime squared equals 0. And there's a couple simplifications that we can already put in given our first result. This r squared becomes capital R squared. This r prime squared goes to 0, and this one becomes capital R squared. And because this whole thing, is the derivative is equal to 0, at the end of the day, we have something that looks like r squared theta prime divided by 1 plus r squared theta prime squared is equal to a constant. And this constant is a constant of integration. Okay? I hope that this equation is familiar. This is exactly the answer that we found in solving for the geodesics on a cylinder. It does raise the question, what happens when we vary with respect to r? Okay? Because this the functional doesn't depend upon z, let's write down the Euler-Lagrange equation of the second kind for the variation with respect to r. So this is or the Lagrange equation of the second kind. Okay? And that looks like square root of 1 plus, and now I'm just going to insert our constraint results. Okay, that's that guy just goes away. That's just f minus r prime times r prime divided by square root 1 plus r squared, theta prime squared. And these are 0. Okay, so all the terms except for the very first one is present. And this whole thing had a d by dz, and that had to vanish. And so that means that we find that 1 plus r squared theta prime squared is equal to some constant, again, a constant of integration. Okay, and it's giving us another equation for theta prime, but one that's in fact degenerate with the equation that we had already found. That is, if we were to insert the prior equation, if we were to insert this expression for theta prime, you would find that a combination of r's and k's was equal to our new constant. That is to say, explicitly we would find that 1 over square root 1 minus k divided by r squared is equal to this new constant of integration. Of course, this is true. The thing on the left is indeed constant because k is a constant of integration and r is constant, the radius of our cylinder, and c is constant. Okay, so this is a trivial relationship between three independent constants. So varying with respect to r actually gave us just a degenerate combination, or it's a degenerate equation with varying with respect to theta. Okay, so we didn't get any more information from having done this. But at the end of the day, the net result is the same. At the end of the day, we had the exact same equation of motion, or equations of motion. Just to summarize, at the end of the day, we had r squared theta prime is equal to a constant. And theta, not theta prime, theta is then going to be equal to some constant times z plus b, where the a and the b are expressed as combinations of k, r, and new constants of integration. Okay, b would be a new constant of integration. You'll note that in none of these do we actually have lambda appearing. Okay, so lambda didn't show up in our equations of motion, and we don't have a value for what lambda looks like. As it turns out, lambda completely falls out of this problem, and that's okay because we didn't need to know lambda in order to solve the problem. All right, so that's our final example today. So the Lagrange multipliers are a particularly convenient way to incorporate constraints into our variational principles in a fashion that makes them appear similar to or identical to adding an additional degree of freedom to the problem. So at the expense of increasing the dimension of our problem by 1, we're able to incorporate our constraints in a seamless and symmetric fashion. So that's the end of the fourth lecture, and I hope everybody has a good day. And remember that the first problem set is due tonight at midnight. All right, goodbye for now.